Hello and hi everyone. My name is Stephen Raj, son of James. My matric number is EI210118. So I'm going to talk about the first subtopic in the logics chapter, which is chapter 1. First is proportional logic. A proportion is a declarative sentence such as if a proportion is true, then we say it has a true value of true. If a proportion is false, it is true value is false. For example, grass is green and 2 plus 5 equals to 5. Proportion. The first proportion is has the true value of true, and the second is got false. That's an example of a proportion. So now we continue with the first subtopic of the logic chapter, which is negation. The negation of a statement is the opposite of the given mathematical statement. If P is a statement, then the negation of statement P is represented by negation P. The symbol used to represent the negation of a statement that is used by the symbol given, and the truth table of a negation have been shown in the slide as well. If got true value is true and the negation of the P is false, same goes with otherwise. Continue with that is conjunction. A conjunction is a statement formed by adding two statements with a connected and. The conjunction P and Q is true when both P and Q are true and is false otherwise. It is shown as the table in the slide as well. Continue with that is disjunction. A disjunction is a statement involving and or. The disjunction P or Q is false when both P and Q are false and is true otherwise. Let P and Q be proportion. The exclusive of P and Q denoted by P exclusive Q is the proportion that is true when exactly one of P and Q is true and is false otherwise, which is known as exclusive. Continue with that, which is conditional, converse, inverse, contrapositive, and biconditional. Which is the conditional statement is if P then Q is called as conditional statement. After that, converse is if P then if Q then only it will get P. That is called converse. Inverse is if not P then not Q. Contrapositive is if not Q then not P will be exist. And finally, which is biconditional, is P if and only if Q.
Hello, my name is So Ying. Matric number is DI210074 from Section 3. What is the tautology and contradiction? Tautology stands for the compound proposition that is always true. Contradiction is the opposite of tautology, which stands for compound proposition always false. Let we see the example. Why P or negation P is true? Because disjunction is true if one or both variables are true. So you see that always true in the truth table. That's called tautology. Why P and negation P is false? Because conjunction is true when both variables are true. That is why this is always false. They call contradiction. Next, logical equivalent. If P, B implication Q is a tautology, the compound proposition P and Q are called logical equivalent. This notation means P and Q are logical equivalent. For example, two values of negation P or Q and P implicate Q agree, they are logical equivalent.
Assalamu alaikum warahmatullahi wabarakatuh. My name is Muhammad Abdurrahman Abdurrahim, number BI20038. I'm going to explain about predicate and quantifiers, which is a subtopic of logic. So predicate, what is a predicate? A predicate is an expression of one or more variables defined on some specific domain. A predicate with variables is not a proposition. For example, the statement x is greater than 1. We don't have the full, what does it mean, x greater than 1? So we have to have, like maybe if x is replaced with a number, let's say 3 greater than 1, that is when it will become a proposition. So, but a predicate with variable is not a proposition. So, for example here, so more generally, a predicate with variables can be made a proposition applying one of the following two operations. First, assigning a value to the variable or quantifying the variable using a quantifier. So other examples of instances or examples of predicates are as follows. Moving on to the quantifiers. What is a Before getting to the quantifiers, we need to understand the meaning of universe of discourse. So the universe of discourse, also called a universe, is the set of objects of interest. So when tackling quantifiers question, you will meet a lot of this term universe of discourse or the domain of discourse. So you need to understand that one first of all. So we have three types of the quantifiers. The first one, the two most important quantifiers are universal quantifier and they exist quantifier, or the symbol is like that one, or it's called existential quantifier. So a universal quantifier, or for all, in an example of a question, man is mortal, can be transformed into the proposition for all x p of x, where p of x is the predicate, which denotes x is mortal, and the universe of discourse is all men. So you can see where the universe of discourse is coming into play. So the next one, the exist or the existential. So for example, some people are dishonest and can, so it can be transformed into the propositional form of there exists x such that p of x. So where p of x is the predicate which denotes x is dishonest, and the universe of discourse is some people. Last but not least, the uniqueness quantifier, or it actually looks like existential, but it has an exclamation mark. So it means that p of x is true for one and only one x in the universe of discourse. That's all from me. Thank you very much.
Negation of a quantific statement. This notation translated into English is understood as there is a S for which PS is 4. When the negation is false, translate to the English language is understood as PS is true for every S. Next, this notation translate into English language is understood as for all S, PS is 4. When the negation is false, translate to the English language is understood as there is a S for which PS is true. Let we see the example. For example, the statement of universal quantification is every child in the class has taken a candy. On quantification, when PS is the statement S has taken a candy and the domain consists of the children in the class. The negation of this statement is not a case that every child in the class has taken a candy. So this is equivalent to a child in the class who has not taken a candy.
Okay, hello, my name is Lee Jin Ho and my matrix number is TI210117. And now I'm going to present about the part nested quantifiers. Okay, first is the definition. Nested quantifiers are often necessary to express the meaning of sentence in English as well as important concepts in computer science and mathematics. Okay, and I prepare an example. Example, every real number has an additive inverses and it can be translated as for all there is plus equal 0. Okay, I think this example is quite easy, so I also prepare another example. Okay, this is example 2. Assume that the domain for the variable x and y consists of all real numbers. The statement for all x for all y, x plus y equals to y plus x. Okay, say that the x plus y equals to y plus x for all real number x and y. Okay, this is the commutative law of commutative law for addition of real numbers. Likewise, the statement for all x there exists y, x plus y equals to 0. Say that for every real number x there is a real number y such as that x plus y equals to 0. Okay, this state that every real number has an additive inverses. Okay, similarly, the statement for all x, for all y, for all z, x plus y plus t equals to x plus y plus t. Okay, the statement is the associative law for addition of real numbers. Okay, I think these two examples is for enough for us to understand this topic, which is uh, which is nested quantifiers. Okay, and that's off my part. Okay, thank you.
Assalamu alaikum warahmatullahi wabarakatuh. My name is Muhammad Abdirahman Abdirahim at trick number BI2100, and today I'm going to explain this subtopic of logics. It's called direct proof. So what is direct proof? A direct proof is a sequence of statements which are either givens or deduction from previous statements, and whose last statement is the conclusion to be proved. Okay, so a direct proof shows that a conditional statement P therefore Q is true by showing that if P is true, then Q must also be true, so that the combination of P true and Q false never occurs. In a direct proof, we assume that P is true and use axioms, definition, previously given theorems, together with rules of inferences to show that Q must also be true. So what does this mean? This means that direct proof or many results are quite straightforward. That is what that means. Okay, for example, if n is even, so is n squared. So assume n, first of all, you assume n is an even number, which n is a universally quantified variable which appears in the statement you are trying to prove. So because n is even, n is equals to 2k for some k. K is extension quantified defined in terms of n, which appears previously. So now n squared is equals to 4k squared is equals to 2k squared. 2k squared. So what are we going to do in the next step? The next step, we're going to say let j be 2k squared, which means that 2k squared there is going to be replaced by j. So j is extensionally quantified defined in terms of k. So in the end, what you're going to say is n squared is 2. That's our conclusion. N squared is equals to 2j. In conclusion, so n is even. So by direct proof, we have proved that if n is even, so is n squared. Thank you. That's all from me.
Okay, so proof by contraposition, which means call a proof by contrapositive, flips the script. Instead of assuming the hypothesis to be true and the proving that the conclusion is also true, we instead assumes that the conclusion to be false and prove that the hypothesis is also false. Remember, we know from our study of equivalence that the conditional statement of P of if P then Q has the same truth value of if not Q then not P. Therefore, a proof by contraposition says let assume not Q is true and let prove not P. And consequently, if we can show not Q then not P to be true, then the statement if P then Q must be true. Okay, for example, if any integer a, if a 3a plus 1 is even, then a is odd. Okay, so by contraposition, it is equivalent to prove if a is even, then 3a plus 1 is odd. We assume a is an even integer. By definition of even integers, a equal 2k for some integers k. Then 3a plus 1 equal 3 bracket 2k bracket cross bracket plus 1 is equal to 2 bracket 3k plus 1 equal to m plus 1 for some integer m such that m equal 3k. This follows that 3a plus 1 equal to m plus, which is by definition an odd integer. Therefore, we have shown that for any integer a, if 3a plus 1 is even, then a is odd by proof of contrapositive. Now, it's time to look at the proof by contradiction. Like contraposition, we will assume that the statement if P then Q to be false. In other words, the negation of P leads to a contradiction because it is negation of P false, then it must be true. The step for proof by contradictions are assume the hypothesis is true and the conclusion to be false. Then show that this assumption is a contradiction to proving the original statement to be true. Okay, for example, for every integer n, if n power of 2 is even, then n is even. Okay, suppose for the sake of contradiction is this is false, assumes there exists an integer n such as if n power of 2 is even, then n is odd. By definition of these integers, n power of 2 equal 2a for some integer a. And by definition of odd integers, n equal 2b plus 1 for some integer b. Then n n power of 2 is equal to 2b plus 1 power of 2. And after that, the 2b plus 1 2b plus 1 close bracket. Okay, because that's power of 2. Okay, after that, 4, it's become 4b power of 2 plus 4b plus 1. Okay, it follows that if n power of 2 equal 2a and n power of 2 equal 4b plus 4b plus 1, then 2a equal 4b power of 2 plus 4b power of 1, 4b plus 1. However, this means that 2a equal 4b power of 2 plus 4b plus 1, there is the negative 1 equal 4b power of 2 plus 4b minus 2a. So after that, it will be negative 1 equal 2 bracket 2b power of 2 plus 2b minus a close bracket. And it will become negative 1 over 2 equal 2b power of 2 plus 2b minus a, which is a contradiction as both a and b are integers. Therefore, for every integers and n, if n power of 2 is even, then n is even also. Thank you.